Hi, George Diamond here. Welcome to our second video on our basic differentiation rules. Now in the first video, we just kind of introduced our four rules, including the big one, right? The power rule for derivatives. Right? So we looked at that particular rule. Now what we're going to look at here in the next video are some examples. I left these out of the first video with the PowerPoint because they don't look as well, but I want to work through some examples with us using the general power rule. Okay, starting with this first one now. So we're going to write the equation of a tangent line to the graph of f of x equals x squared whenever x equals -2. So we're going to write now we're not just going to get the slope, but we're actually going to write the equation of a tangent line to the graph of f of x equals x squared. Now to start off with, to write the equation of any line, you need two things. You need the slope and you need a point on the curve. Now, we're given x equal -2, so we're given the x value, but not the y value, so we need to get y. So let's generate us a function value here. F of -2 would be -2 squared, or 4. So our corresponding y value is going to be 4. So remember now, to write the equation of a line, okay, you have to know one point on the line, right, in order to write the equation, and you need to know the slope. Now the slope, we're going to use the derivative to get the slope. Right, now, the derivative of f of x equals x squared, remember the general power rule? Okay, the derivative is going to be 2x. Right, now, the x value is -2, so to get our slope, all we have to do is substitute -2 in. It would be 2 times -2 or -4. Now, so the slope at x equals -2 should be -4. Now, to write the equation, you can use the point-slope form of your equation. Remember the point-slope form? Y minus y1 equals the slope times x minus x of 1. Right? So using your point, okay, this will be y minus 4 equals the slope. Now we got the slope is -4, so it'll be -4 times x minus a -2. Now minus and negative, we'll change that to plus a positive. We end up with y equals to y minus. So y minus 4 equals -4x minus 8. Add 4 to both sides, we have y equals -4x. So adding 4 to both sides, let's see now, this would be a -8. Adding 4 to both sides gives us -4x minus 4. And that'll be the equation of our line in slope-intercept form. Okay, let's try another example. So let's find the derivative of v. So this is a bunch of derivatives, right? We didn't do very many of them on the previous video, right? Because this is just a PowerPoint, really. But let's see if we can take a look at some derivatives. Now this is practice basically using the general power rule for derivatives. Now f of x equals 4/5 t to the 3rd power. As you get your derivative, so remember we said we have a 4/5 is your coefficient basically. So it would be 4/5 times 3 times t to the 3 minus 1 power. So you're going to bring the 3 down, multiply it to your coefficient, and then subtract 1 from your exponent to get the new exponent on your derivative. Now 4/3 times, or 4/5 times 3 gives us 12/5. T to the 2nd power, that's your derivative. All right. So once again, this is just the general power rule for derivatives. Let's try another one. Okay, let's try a radical. Remember with the general power rule, you have to subtract 1 from your exponent. So with any type of function, really, we need to rewrite it with exponents in exponential notation. So any type of a radical, okay, we're going to write it in exponential notation. So y equals 2 to the square root times the square root of x is the same thing as y equals 2x to the 1/2 power. Right? So since there's a little square root is x to the 1/2 power. Now, once you rewrite it in exponential form, now let's use the general power rule for derivatives. So the derivative here is going to be 2 times 1/2 x to the 1/2 minus 1 power. Now, 2 times 1/2, these cancel out, gives you x to the, now 1/2 minus 1 is -1/2. Right, so the x to the -1/2, which is the same thing as 1 over x to the positive 1/2, which is also equal to 1 over the square root of x. So if you want to write it back in radical notation, this is what the radical answer will look like. So the x to the -1/2, which is the same thing as 1 over x to the positive 1/2, or 1 over the square root of x. Try another one. Now we're just running through these quickly, right? This is just practice again. Okay, what about 1 over 2 times the cube root of x? Right, now, let's rewrite this. Now, a lot of times you notice with derivatives, the hard part really is getting it in exponential form so we can easily take the derivative. So let's do, now let's see, with this one right here, I want to rewrite this. This will be 1 over 2x to the 2/3 power. Right, so to convert your cube root here, it's x to the 2nd power, so it'll be 2 divided by 3. So it'll be x to the 2/3 power. And let's pull the 1/2 off. Now this will be 1/2 x to the negative 2/3 power. Right, so rewriting. So I want to rewrite my original expression in exponential form. So we can pull the 1/2 off times, since x to the 2/3 is at the bottom of your fraction, it'll be x to the negative 2/3 power. Okay, now we can quickly take the derivative of this. Right, this will be 1/2 times negative 2/3 x to the, and we're going to subtract 1 from our exponent here to get the new exponent. Now, negative 2/3 minus 1 is negative 2/3 minus 3 over 3. Now, so you subtract 1 from negative 2/3, which is negative 5/3. So the new exponent here will be negative 5/3. And then multiplying, as you multiply the two fractions, the 2's cancel out. And so give us negative 1/3 x to the negative 5/3. So the new exponent is negative 5/3. So 1/3 x to the negative 5/3 power. And that's our derivative. Okay, let's try another one. Okay, let's take 5 over 2x cubed. Right, let's try this one. Now, once again, I want to pull the 5/2 off this fraction. I'm going to write it as 5 over 2 times 1 over x cubed. Right, so pull the 5/2 off. Now, you know that 1 over x cubed is the same thing as x to the negative 1, right? So this will be 5/2 times x to the negative 3. So 1 over x to the 3rd power is the same thing as x to the negative 3 power. Now, this is y. Now, the derivative, y prime, will be negative 3 times 5/2, which would be negative 15 over 2. x2, now you got to subtract 1 from your exponent, be to the negative 4 power, and that's your derivative. Now, you can rewrite this. If you rewrite it without the negative exponent, this would be 15 over 2x to the positive 4 power. So that negative exponent is going to end up in the bottom of your fraction there. Okay, let's try another one. Okay, let's try this one here. Now, first of all, let's go ahead and simplify our powers. This is 5 over the quantity 2x cubed. Okay, this will be 5 over, now 2 cubed is 8, so it'll be 8x to the 3rd power. Now, I'm going to do this one just like we did the other one. Let's pull the 5/8 off. So it'll be 5/8 times 1 over x to the 3rd power, and which is equivalent to 5/8 x to the negative 3 power. Right, now this is y. Now, we're ready to take our derivative. Right, so as we find our derivative, y prime is going to be equal to, now negative 3 times 5/8 gives us negative 15/8 x to the, subtract 1 from your exponent, it'll be x to the negative 4 power. And that's our derivative. Now to rewrite it again, this will be negative 15 over 8x to the 4th power. So if you write it without the negative exponent will end up on the bottom of your fraction. Let's try another one. Now let's try 7 over 3x to the negative 2. Now remember, anytime you have a factor with a negative exponent in a fraction, you can move it to the other part of the fraction. So I'm going to move this negative 2 exponent to the top of the fraction, and it becomes 7x squared over 3. Now, 7x squared over 3 is equivalent to, I'm going to rewrite this, pull the 7/3 off. This would be 7 over 3 x to the 2nd power. So the same thing as 7/3 times x to the positive 2 power. Now, let's use the general power rule. 2 times 7/3, as we get our derivative, gives us 14 over 3 x to the, now subtract 1 from your exponent, gives you x to the 1st power, or just 14/3 x. And there you got it. So very quickly, you can get your derivative. Let's try another one. Okay, let's try this one here. Now this time we have, in the bottom of our fraction, we have 7 over the quantity 3x to the negative 2 power. So I'll tell you what, let's do now. Let's move this entire expression to our numerator. And it becomes 7 times 3x to the positive 2 over 1. So there's basically nothing left in the bottom of that fraction. And the the function becomes 7 times 3x to the second, quantity 3x to the second power now. Now, let's start off, let's go ahead and simplify our powers first. This is now 7 times 3 squared gives us 9, x to the second power. And then last, 9 times 7 gives us 63, x to the second as you simplify. So to get it simplified, we end up here now with y equals 63x to the second power. And then last, to find our derivative, 63 times 2 would be 126x. Subtract 1 from your exponent would be 126x. So that's our derivative. And let's try this another one. Let's try another radical problem. Now I said radicals, we really don't work with them until we convert them to rational exponent form. So we don't want the radical form. We want it with the exponent so that we can use the general power rule. Now we got 4 over the 5th root of x to the 3rd power. Now let's rewrite this so that it's no longer in radical form. This will be 4 over, and this will be x to the 3/5 power. Now let's pull the 4 off, and this becomes y equals 4 times 1 over x to the 3/5, right? And then 1 over x to the 3/5 is the same thing as x to the negative 3/5 power. So this is 4x to the negative 3/5 power. Okay, so really with a problem like this, like I said, it's basically just a matter of rewriting it. So it's no longer written in radical form, but rational exponent form, right? And then we're going to rewrite it with the negative exponent here. So now it's ready to use the general power rule. Okay, we have an exponent, we can multiply it to the coefficient, subtract 1. So as we get our derivative now, the derivative is going to be negative 3/5 times 4. So it'll be 4 times negative 3/5. Negative 3/5 times x to the negative 3/5 minus 1. Now, 4 times negative 3/5, nothing simplifies. That'll be negative 12/5. Now, as you subtract subtract 1 from negative 3/5. Now, negative 3/5 is already negative, so this would be negative 3/5 minus 5 over 5, or negative 8/5. So as you subtract 1 from this negative fraction now, negative 3/5 minus 1, or 5 over 5, I'm going to rewrite it with the same denominator, gives us negative 8/5. So the new exponent will be x to the negative 8/5. Now I'm going to leave it written with the negative exponent there, but that would be our derivative. Okay, let's try another one. Now, like I said, we're quickly looking at a bunch of these. We have a bunch of them to look at, so we'll just run through them quickly. Now, let's put this one in the correct form. Now, later on, this is later on we can use a different rule to take the derivative of the quantity 3x minus 1 to the second power. But right now, we're going to have to see if we can simplify this another way. So let's rewrite this. This will be y equals, now this is just a binomial squared. This is 3x minus 1 times itself. Now let's multiply this out, and to multiply a binomial times itself, you just use the FOIL method. That will work fine. So multiply your first terms. 3x times 3x gives us 9x squared. 3x times negative 1 is negative 3x. Negative 1 times 3x is negative 3x. Negative 1 times negative 1 gives you positive 1. Now combine like terms. We have y equals 9x squared minus 6x plus 1. Now we multiplied the binomial times itself, we expanded it and multiplied it. Now we have a little polynomial here. This is all this is. Let's use the general power rule. Now we're going to get our derivative. So y prime. So y prime, let's take the derivative of the first term. So the derivative of 9x squared would be 18x. And the derivative of negative 6x, remember an x expression like this, all you do is drop the x variable, will be minus 6. And the derivative of 1 is 0. So the derivative of any constant is 0. There you go. So that's our derivative. Now take a look at this one here. Now this time we have what? 2x squared minus 3x plus 1 divided by x. Now with some of these problems we're looking at today, the hardest part really is simplifying them and getting them in the right form that we can take the derivative of. Now here we have, it's like a little trinomial with a monomial divisor. Right, so what we want to do is, let's divide each one of those terms by x. Right, so this will be equivalent to 2x squared over x minus 3x over x plus 1 over x. Now let's simplify these. 2x squared over x, X will cancel, and it gives us 2x. And here the x's will cancel, be minus 3. Plus, now 1 over x, let's see if we can rewrite this one with the negative exponent. This will be x to the negative 1 power. All right, so we've already looked at that. So we've taken this expression, a fraction, divided it out here. Now we have this expression here. Much easier to take the derivative of. So let's take the derivative of each term, starting with, now this is h of x, so h prime x is going to be equal to, now the derivative of 2x is 2. Now the derivative of negative 3 is 0. That's a constant. Remember the constant rule? The derivative of any constant is 0. Now the derivative of x to the negative 1, let's bring the negative 1 down. It'll be minus x. And you got to subtract 1 from your exponent, it'll be to the negative 2 power. So that's the derivative. It's going to be 2 minus x to the negative 2 power. Now if you want to, you can write this as 2 minus x squared, 1 over x squared. So you can write it like that if you want to. Let's try another. Okay, let's take a look at our next derivative example. Now, with this next problem, this is problem number 12, said we're going to find the slope of a function at the point 218. So we're not just getting the derivative this time, we're going to get the slope at a particular point on our curve. So this is the slope of our tangent line at that particular point on our curve. So remember, our slope is the derivative is slope. So the derivative will tell us the slope at any particular point. If we know the x value, we can just substitute it in. Now, a lot of times with these problems that we're looking at here, a lot of functions, the hardest part is getting it in the right form. So we can take the derivative and use the general power rule. Remember, the general power rule uses the exponent. The exponent times the coefficient, subtract 1 from your exponent. So, so typically with a lot of problems, we're going to have to rewrite them so that they're in exponential form. Now this problem right here, we just have to do a little multiplication. So we've got f of x equals 3x times the quantity x squared minus 2 over x. So all we have to do here is remove our parentheses. We should be ready to take the derivative. So let's take the 3x, you multiply it to both of our terms, and that'll give us f of x is equal to, it'll be 3x cubed minus, now if you multiply 3x times 2 over x, the x's cancel out. That gives us 3 times 2, which is 6. So our simplified function then, after we multiply the 3x inside our parentheses, we end up with 3x to the 3rd power. This is a 3. So 3x cubed. There goes 3x cubed minus 6. And as you multiply to this fraction, the x's are going to cancel out. That just gives us 3 times 2. Now we're ready to find our derivative. Right, so to get our derivative, the derivative of 3x cubed will give us, what, 9x squared. Once again, multiply the exponent times the coefficient, subtract 1 from your exponent. So you got to subtract 1 from your power, and that'll give us 9x to the 2nd power. Remember, the derivative of 6 is 0. 6 is a constant. Think of the graph of y equals 6 as being a horizontal line, right? The slope of a horizontal line is 0, so the derivative of 6 is 0. So think of a number or a constant. And just imagine the graph is always a horizontal line. So the derivative of any constant is 0. Okay, now we've got our derivative. We're ready to get our slope now. So to get our slope, we're going to substitute 2 in at x equal 2. All right, so plugging these in, it'll be 9 times 2 squared, which would be 9 times 4, or 36. So our slope would be 36. That would be 36 over 1. That would be a rise of 36 and a run of 2. So that would be the slope of your tangent line to your curve, would be 36. Okay, let's try our next problem. So we have several more problems we're doing. We're just doing some examples, of using the general power rule for derivatives. This is another one. Let's take a look at this one right here. Now the last problem, we had to find the slope of our tangent line. Now this one goes a little bit further. So we're going to write the equation of the tangent line to the graph of y equals x squared plus 2x times the quantity x plus 1 at the point 1, 6. Now, to get this function in the correct form to take the derivative, we've got to multiply these two binomials together. So let's go and do our multiplication. Now, to multiply the two binomials, you just have to use the FOIL method. So multiply x squared times x will give us x to the 3rd power. X squared times 1 will give us x to the x squared. Multiply the inside terms. 2x times x will give us 2x squared. So we plus 2x squared. And then plus 2x times 1, multiply your last terms, gives us 2x. All right, so multiplying the two binomials, just use your for method. After that, we've got to combine like terms, then we've got a couple of x squared terms we need to combine. So we have y equals x to the third power, okay, plus, and what is that, 3x squared, okay, plus 2x. Okay, so we multiply these using our for method, so x squared times 1 gives us, or x squared times x gives us x to the third, x squared times 1 is x squared, 2x times x is 2x squared, and then 2x times 1 gives you 2x. We've got our like terms combined, so we've done that. Okay, now we're ready to take our derivative. So let's get our derivative here, and this will be, our derivative will be, I'm taking the derivative of the first term, the derivative of x cubed, we bring the 3 down front, and then subtract 1 from your exponent would be 3x to the second power. Now do the same thing to the second term. It would be plus 3 times 2 gives you 6, x to the, now subtract 1 from the exponent will just give us 6x. Now the derivative of 2x, remember, is just 2. Okay, you just have a single variable, no power really, other than 1, so just the derivative of 2x is just 2. Basically, you just drop the x as you take your derivative. I said now, very quickly now, we've got our derivative here on this particular problem. All right, and come on back here, we are. Okay, now let's see, we're ready to write our equation. Now this time, let's write this equation in point-slope form. So remember point-slope form, y minus y1 equals a slope times x minus x1. Okay, because we've got everything except for the slope. So as you set this up, this will be y equals, y minus the y value, which is 6, equals whatever the slope is times x minus x1. Now x1 is 1, so it'll be x minus 1. Now, what's missing here is our slope. Now, we're going to use our derivative to get the slope. So we've got the derivative already. So we calculated our slope now. Now, this will be the slope at x equals 1. So all we have to do now is plug in the 1. That'll give us our slope, and we'll have our equation written in point-slope form. So substituting 1 in will give us, what, 3 times 1 squared plus 6 times 1 plus 2. And what is that? 3 plus 6 plus 2 gives us 9, 10, 11. So we have a slope of 11. So let's go and put that in. Let's put it with a slope of 11. Okay. And we've got our equation written. Now you can convert it to a slope-intercept form if you need the other form or standard form. But this will be point-slope form. Okay, let's try this another one. Okay, let's try finding the derivative of this expression here. All right, now you look at this, right away you see these radicals. I always tell my students, you know, as you're writing the problem down, you want to convert the radicals to rational exponent form. So we don't work with the radicals without changing forms. Because remember now, we're going to use the general power rule, okay, not the longhand derivative formula anymore. We're using the general power rule. The general power rule uses the exponent. So the exponent times the coefficient minus 1 from the exponent. So so almost all radical problems, as you write them down, just go ahead and convert them to rational exponent form. Now underneath the radical, this is x to the first and x to the first here. So let's rewrite them in what we call rational exponent form. This will be y equals x to the 1/3 power plus this will be x to the 1/5 power. So instead of the radical form, we got it in fractional exponent form, if you will. Right, now, we're ready to take our derivative now, right? So we'll just use our general power rule, and that's all we're doing here is just getting the derivative. We're not getting the slope or anything, just an expression for our derivative. So our derivative is going to be, now finding the derivative of the first term, we'll bring the 1/3 down, times x to the, now we got to subtract 1 from 1/3. Come over here now, 1/3 minus 1 is 1/3 minus 3/3, which is negative 2/3. Now, so our new exponent then becomes x to the negative 2/3 power. So you get a negative exponent when you subtract 1 from 1/3. Now, plus, let me erase this. Now, let's take the derivative of x to the 1/5. We'll do the same thing, bring the 1/5 down. x2, now this time we're going to subtract 1 from our exponent here. Will be 1/5 minus 5/5, which would be negative 4/5. So as you subtract 1 from 1/5, we're going to rewrite it as 5/5, so it has the same denominator, right, as the other fraction, and then go ahead and subtract them, so this will be negative 4/5. And there you've got it. Now, I'll tell you what, let's do this, see if we can rewrite these. Okay, without the negative exponent. So technically, you don't want to leave a negative exponent like this in an expression or in a function like we have here. So we have y prime will be equal to, let's see now, the factor with the negative exponent is going to go to the bottom of a fraction. This will be 1 over 3x to the 2/5 or 2/3 power plus this will be 1 over 5x to the 4/5 power. Now, so remember, as you rewrite these negative exponent with a fraction like this, the x to the 2/3 goes to the bottom of your fraction with the 3. The 3 is already on the bottom of the fraction. The 1's on top. So you need 1 over 3x to the positive 2/3 power. Right. And let's do one more thing. Let's see if we can rewrite this in radical form. So what if they're looking for that? If this were a multiple choice question, let's say on the AP Calculus exam, what would be the answer in radical form? So in radical form, this would be, let's say, or. This would be 1 over 3 times, you know, the bottom of the exponent becomes your new index. It would be 3x squared under your radical plus, this would be 1 over 5x to the, so 5 times the 5th root of x to the 4th power. So if you got to rewrite it all the way into radical, back into radical form, this is the way it will look. So it's easy enough. Get your rational exponent to get a derivative, then from rational exponent form to radical form is easy enough. Okay, let's try another problem here. Let's try number 15. Try a trig problem, right? So trig expression as you take a derivative. Now remember from our previous video, okay, we said the derivative of sine is cosine. The derivative of cosine is negative sine. Now those two you need to have those memorized. So when you come across a problem like this, you can very quickly take the derivative. So let's start off. All we're looking for here is the derivative. Now to get the derivative of x is 1. Right, so the derivative of x is 1. So the coefficient is 1. So basically you drop the x and leave the coefficient. So it'll be just 1. Now the derivative of cosine is negative sine. So it'll be 1, in this case it'll be 1 minus now. So instead of plus, it'll be minus sine x. And that's our derivative. So the derivative of cosine is negative sine, so it'll be 1 minus sine x. There you go. Now if we needed to get the slope at a particular point, all we have to do is substitute in for x. Okay, let's try example number 16. Now another trig function here. Once again, we're just getting the derivative. So y prime is going to be equal to, and this is 2 sine x plus 3 cosine x. Now once again, as you take the derivative of 2 sine x, this will be, now the derivative of sine is cosine, so it'll be 2 cosine x. So that's the derivative of our first term. The derivative of sine is cosine, so it'll be 2 cosine x. Right, the coefficient, the 2, the constant multiple there, you just bring that down. Now the derivative of cosine is negative sine, so it'll be minus 3 sine x. And there you go. Now this can't be simplified. That's it. So that's our derivative. Okay, easy. Now you got to remember, the derivative of sine is cosine, and the derivative of cosine is negative sine. So those two you have to have memorized. And we'll be looking at the other trig functions later. You're going to have those memorized also. Okay, let's look at the next one here. So another trig problem. Now this time, let's see if we can get the slope at pi negative 1. Now this time we have g of t equals 2 plus 3 cosine t. So we're going to get our slope at pi negative 1. Now remember, to get our slope is the derivative. So let's get our derivative first. So g prime t. Now first of all, the derivative of 2, 0. That's a constant. Right? So like I said, 2, the graph of 2 would be a horizontal line, 0 slope. So the derivative of 2 is 0. So this would be 0 plus, well, I'll just leave the 0 off. I think we don't need to put the 0 in. Now the derivative of cosine is negative sine. So bring the 3 down, and then sine t. Okay, that's our derivative. So the derivative is 0 minus 3 sine t, and we just drop the 0. You know, that's our derivative. Now let's go and get our slope now. So this is the slope at t equals pi. Now, once again, substitute pi in for t. This will be negative 3 sine pi. Right. Now, remember from the unit circle, okay, pi is here. Okay, that's the point negative 1, 0. Sine is going to be your y component, so sine is going to be 0. So sine of pi is 0. So what we end up with is negative 3 times 0, or a 0 slope. Now that would indicate a horizontal tangent line to our curve at 0. Right? We have a slope of 0 at pi for this particular function. Okay, let's try another one. All right, this is a good one. Now we're going to do an average velocity problem. All right, it says a ball is dropped from a height of 100 feet. Its height s at time t is given by the position function s equals negative 16t squared plus 100. Where s, the position, is measured in feet and time is measured in seconds. Now we're going to find the average velocity over the time interval from 1 to 2. So the average velocity. Now, if you can imagine, okay, here's our position function, negative 16t squared plus 100. Now, if you can imagine, let me see if I can sketch a little potential graph that we're looking at here. This is in feet and seconds, so this is a distance time graph kind of. So this would be feet. Feet time is in seconds, so feet in seconds. Okay. Now, if you were to, a version of the graph would look something like this right here. Right? So it starts off at 100. That would be the height. Right? So the number on the end would be the height. Starting off with an initial velocity of 0, so there is no middle term in your position function. Now, what we're trying to get here, if you can imagine, from 1 second to 2 seconds. All right, so we got a ball being dropped right from a height. So a ball is dropped from a height of 100 feet. All right, so from 1 second to 2 seconds, what would be the average velocity? So from 1 to 2, come on up here. 2 would be about right here. Right, so you're looking at, so when you get the average velocity now, the average velocity is simply the slope of the secant line on your time distance curve from 1 to 2 seconds. All right, so all we're looking for here is the slope. All right, so we're just looking for the slope of our secant line, okay, from 1 to 2 seconds. Remember, the slope of your secant line is, our slope is simply y2 minus y1 over x2 minus x1. So with our position function here, this would be the position s of t2. If you remember from your pre-calculus class, this is the way they express the average velocity, s of t2 minus s of t1 divided by t2 minus t1. So this would give us the average velocity. So basically, as we set this up, so we're going to erase this. So we're looking for our slope. So erase here. I don't think we need the graph anymore either. All right. There we go. All right, now let's see, we're looking for the position s of 2 minus the position at 1 divided by 2 minus 1. So this is what we're going to calculate. So let's substitute 2 into our function for t, substitute 1 into our function for t. That'll give us the position at 2 seconds and 1 second. And then do a little subtraction. So as we set this up, okay, this will be, put this in brackets. This will be negative 16. So negative 16t squared. Erase that. Negative 16 times 2 squared. Now, s of 2, remember, you're just substituting 2 into your position function for t, plus 100, minus the position at 1. Right? So the position at 1, we're going to substitute 1 in for t. So it'll be negative 16 times 1 squared plus 100. Right, so the position at 2 minus the position at 1, and you use your position function to calculate those. All those divided by 2 minus 1. Now, watch your units now as you set this up. You want to watch your units. The position is in feet, so this will be in feet minus feet. On the bottom here is seconds minus seconds. All right, so we get our average velocity should be in feet per second. Okay, let's see what we have. 16 times 4 would be 36 plus 100 would be, so 36 would be 64, would it? So it would be 64, so 4 would be 64 plus 100, which would be 36 minus, okay, this would be negative 16 plus 100, which would be 84, so minus 84, divided by 1, which would be negative 48, it would be negative 48 feet per 1 second. So as you do your calculation there, okay, this will be our average velocity. So negative 48 feet per 1 second, or just negative 48 feet per second. So that'll be our average velocity. Remember, this is the slope of our secant line on your distance time curve. All right, let's see. Let's try another problem. So, okay, let's try one involving instantaneous velocity. All right. So instantaneous velocity now says at time t equals 0, a diver jumps from a diving board that is 32 feet above the water. Okay, the position of the diver is described with this function right here. So the position of the diver described as s of t equals negative 16t squared plus 16t plus 32. Now this time we're looking at, we're going to be looking for instantaneous velocity now. Now instantaneous velocity, we use the derivative. Okay, now we're talking about slope of a tangent line. So instantaneous velocity US velocity. Okay, velocity, if you can imagine a distance time curve. So if you imagine a distance time curve, this is at a particular time interval, all right? So this would be a point on our curve. Now, at instantaneous velocity, you can imagine this is our point. And this time we're looking for the slope of our tangent line to the curve, not the slope of the secant line. Average velocity, you use just a slope formula basically, all right? Now this time we got to use our derivative. So this is our slope of our tangent line. So the slope of our tangent line, and this time we have to use the derivative. Now, so we get instantaneous velocity now at a particular instant in time. All right? We got to use our we use the derivative. So let's take a look and see what all our problem is asking for now. Our position function s of t equals negative 16t squared plus 16t plus 32. Now s of t is in feet and time again is in seconds. So let's come on over. Now first question. Okay, when does the diver hit the water? All right, now he's going to hit the water. The diver is going to hit the water when s of t equals 0. So let's let this be 0. That'll equal negative 16t squared plus 16t plus 32. So we got to figure out, first of all, when's the diver going to hit the water? Okay, now he hits the water when the position, his position will be at 0 height. Right, so let's substitute 0 in for s of t. Now we're going to solve this for t. Now this is a quadratic function, so we're going to have two time values, all right? Now first of all, let's factor off a common factor, so as we solve this, and I want the leading coefficient on my quadratic function needs to be positive. So I'm going to factor off the negative 16 off the first term. That will leave us with positive t squared minus factoring 16 off the middle, negative 16 off the middle term, make that a minus t, and then factoring 16 off the 32, a negative 16 off the 32 would be minus 2. So inside our parentheses now, I'm going to change the signs on each of those terms. It'll be a positive t squared minus t minus 2. Okay, now let's go ahead and factor. Now the negative 16, we can, as far as our time values go, we don't use the negative 16. That's just a number. We can kind of forget about that. And it's going to solve the t squared minus t minus 2 for t. Now, I want to see if this, I think this can be solved by factoring. This will be t and t. This will be 2 and 1. All right, now let's see, the middle term of your coefficient is a negative 1. So that means that the 2 has to be minus. So the larger number is going to be negative, and the 1 has to be plus. So to get our time values now, let's take t plus 1 equals 0, or t minus 2 equals 0. So set each of those equal to 0. Go down. Now solving for t, we end up with t equals negative 1 seconds. Over here we end up with t equals positive 2 seconds. All right. Now I'm sure everybody recognizes, time's not going to be negative. So the negative 1, okay, we're not going to use. Let's just cross this one out. So time can't be negative, all right, so we'll get rid of that one. So the diver must hit the water at 2 seconds. So this is what we're looking for. So the diver's going to hit the water after 2 seconds. All right, so that's the first part of our problem now. We've got to figure out when the diver hits the water. Okay, next. Okay, what's the diver's velocity when he impacts the water? So what's the diver's velocity when he impacts the water? Okay, so you can imagine now, a distance time curve, right? And this is our graph, 32, 32. And this is our graph. Now, this is when he hits the water, so if you can imagine, we're looking for the slope of that tangent line as he impacts the water, all right? So as he impacts the water. So I'm going to erase this, I just wanted to mention, all right. Okay, yeah, what's the diver's velocity when he impacts the water? Now this time we need the derivative, so let's get the derivative of our position function. The derivative of negative 16t squared, 2 times negative 16 is negative 32t. So we're using our general power rule again. Multiply your exponent times your coefficient. Subtract 1 from your exponent will be negative 32t to the first power. All right. The derivative of 16t is just 16. So remember now, you drop the variable. All right. So if you just have one variable, a power of 1, you just drop the variable. So this is our derivative now. This represents, this is now an expression for our instantaneous velocity. Okay, we can get the slope of any tangent line to our position on our position curve using this expression now. So when does he impact the when does the diver impact the water? So he impacts the water. That's going to be our slope of our tangent line, if you will. So this would be basically getting our slope. Okay, we said he impacts the water at t equals 2 seconds. So let's take the 2, plug it in, let's see what we get for our slope. It'll be negative 32 times t times 2 plus 16, which would be negative 64 plus 16. So negative 64 plus 16, which is negative 48 feet per second. So negative 48 feet per, another answer with negative 48. I didn't plan for like 3 answers in a row to be negative 48, but that would be that would be the instantaneous velocity when the diver hits the water. Okay, let's move on. We got one more problem. This will be our last one with this last example we're going to look at here on our video. So I'm going to try one of these. This is kind of an application involving a volume formula. So the volume of a cube is given by V equals S cubed. Okay, find the rate of change of the volume with respect to S when S is 4 centimeters. This is kind of odd, because instead of x and y, all right, now we're working with v and s. So now you notice in velocity, as we go through the course from time to time, we'll have to take the derivative, some of our geometry formulas. All right, so what we have here, represents our rate of change. Now, rate of change represents slope. So we're talking about the slope again, all right? The slope of, or the rate of change of the volume with respect to s. So instead of the rate of change of y with respect to x, we're going to take the derivative of the volume with respect to s. So as we set this up, this will be dv over ds. All right, so the rate of change, so the derivative of the volume with respect to the side, okay, equals. Now let's use our general power rule to take the derivative of the right-hand side. This will be 3s squared. Now this is our rate of change. So it will be our slope, our general rate of change. Rate of change is the derivative is slope. All right. Now at 4 centimeters, this will be 3 times 4 squared, which would be 3 times 16, okay, or 48. That would be in centimeters cubed for our unit. So it would be 48 cubic centimeters. 48 again. Once again, I didn't plan for each of these answers to be 48, but there's another one. Once again, it's kind of odd because now we're taking the derivative of a formula, so an actual geometric formula. Okay, V equals S cubed. And we're finding the rate of change of the volume with respect to the side is represented as 3 times the side squared. And to get the rate of change at 4 centimeters, all you do is plug it in, and that gives us our rate of change. So it's changing at a rate of 48 cubic centimeters. And that completes our examples. Hopefully these examples have been helpful as we look at some of our homework problems and stuff. Hopefully these will be helpful.